In this video, we will learn how to solve linear programming models using Excel Solver. We will work on the Excel file and refer to the instructions in the Word file. The Word file looks like this, and the Excel file looks like this. First, we'll learn how to solve the first example, RMC. There are two steps in solving linear programming models. First, you need to set up the model on Excel spreadsheet. Second, we need to get Excel Solver to solve the model that we set up. In RMC example, remember there were two products, fuel additive and solvent base. And the decision variables were F and S, meaning F was the tons of fuel additive to produce and S was the tons of solvent base to produce. We wanted to maximize the total profit from these two products. Shown here is a profit function 40F plus 30S, where 40 and 30 were the unit profits. And we had constraints representing the materials that were available to make these products. So materials 1, 2, and 3, here were the available amounts. And these three constraints said the amount of material used must be less than or equal to the amount that was available for each of the three materials. Now this is the Excel model after the problem has been solved. And the steps that we need to create this result are all shown here in your Word file. I will demonstrate all these steps on the Excel file, so let's go over to that file. Notice the layout of the model, and also notice that I also copied down the LP model here. The variables are in columns. We got the column for fuel additive, columns for solvent base, and the objective function and the three constraints are in rows. We designate the cells here for the decision variables, and the coefficients here are entered in separate cells. And then we construct the formulas like these by putting together the coefficients and the variables using the sum product function. For the purpose of demonstration, we'll delete all the values and formulas, but let's leave the headings like column headings and the row headings so we don't have to type them again. I'm going to delete all the numbers and the formulas like this. Now let's follow the steps. So it says here, row headings, column headings, we have those. Coefficients for the objective function and the constraints. The objective function coefficients are here, 40 and 30, and the coefficients for the constraints are here, 0.4, 0.5. Then nothing for F and 0.2 for S. And then 0.6 and 0.3. Now in step 2, we designate a location where the answers will be stored. So there are two cells we designate as variable cells, and those cells are going to hold the values of the decision variables F and S. I've already designated these cells, B4 and C4, as the variable cells. Now you want to highlight these cells in some way, like you might shade them in your favorite color. I like the rosé color. Or you might put a border around them, or you might do both, like I did. Now, after you run Solver, it will automatically place here the optimal solution. For now, you could either leave them blank or put some test values in here. Now, I'm going to try the values we tried before. Let's see, maybe try F of 20 and S of 10. Now, having some numbers in here helps us check when we put in the formulas whether the formulas are working correctly. Step 3, we designate a location for the objective function and then put in the sum product function in there for the expression 40F plus 30S. So here we're going to put the objective function, that is 40F plus 30S. Now, if you didn't know about the sum product function, you might be inclined to type something like this, cell 40 times F plus 30 times S, okay, which gives us 1100, which is correct. But don't do it. It's more efficient to use a sum product function. Now, remember what the sum product function does. When you give the sum product function two cell ranges, that is two lists of cells, for instance, give it like 40 and 30, and F and S. Then it'll multiply each corresponding pair and then sum the results. So that is, it'll multiply 40 and F, first cells, and then multiply 30 and S, the second cells in the list, and then add the results together. So it will do here 40 times F, and then it'll do 30 times S, then it will sum the products, so plus. So I'm going to go over here and enter the corresponding formula. Now 40 and 30, that's here. Select these two cells. And then F and S are here. Select these other two cells. So what this will do is it's going to go B6 times B4 plus C6 times C4. Or in terms of values, it will calculate 40 times 20 plus 30 times 10. So that would be what? 40 times 20 is 800. 30 times 10 is 300. 800 plus 300 should be 1100. Fourth step, again we use the sum product function to write down the left-hand side expressions of the constraints. So here we would type sum product. Now we want to go 0.4f plus 0.5s, so it's coefficients first, and then comma, and then the variables. Now we plan to copy down this formula to the other rows, to the other constraints. So what do we need to do before we move on? Right, we need to fix these cells, because if we didn't fix these cells and we just copy down the formula, then the reference to B4 to C4 will move to B5 to C5 and B6 to C6, and that would not make sense. We want to fix the reference to the variable cells. So we could use a function key F4 to put in the dollar signs. If I hit F4 again, it gives me only $2, and hit it again gives me $2 in different locations, and hit it again, no dollar signs. So it's a toggle key. Now if we have dollar signs everywhere like this, that indicates absolute reference, meaning no matter what we do, the addresses B4 to C4 will stay the same. Now if I have dollar signs only to the left of the row number, that means it'll fix the row reference, but not the column reference, which is what we want, because as I copy down the formula, I just need to make sure that this row number 4 doesn't change to row 5 and row 6. Now let's check. So you could see that it still refers to the correct variable cells. Now it would have been fine if I had placed dollar signs both to the left of the column. Now it would have been fine. Well, it would have been fine if I put dollar signs in both places, next to the column reference and next to the row reference, like this. Like this. So if you're not quite sure where to put the dollar signs, it's fine if you just put them in both places, then you'll be safe. This will just give me the same result. In general, the dollar signs should be placed immediately to the left of what you want to lock. So if I were copying this formula across the row, and I wanted the column reference to stay the same at B and C, then I will put the dollar signs next to the B and C, like this. So when you put the dollar signs only to the left of the column number or only to the left of row number, that's called mixed reference. Now if you're confused by any of this, then just feel free to put dollar signs everywhere, create an absolute reference like this. You would still get the same result, so that's fine if you did it that way. These three cells are the left-hand sides of the three constraints here. Now we indicate the types of the three constraints here with the inequality signs. So here I put in less than or equal to, and here it's all less than or equal to, so I'm just going to copy that. I'm just going to copy that down. Now the right-hand sides is 25 and 21. Enter those values. So what we've done is we've done steps 4, 5, and 6. Now we're at step number 7, where it says optional. Now this part is optional, but it gives you helpful additional information. We could keep track of the leftover materials by means of a slack column. For instance, maybe we want to see, with this tentative solution, how much materials will be left over. That is, materials 1, 2, and 3, how much will be left over of each. Well, here, now this number 13 says, if you make 20 tons of fuel additive and 10 tons of solvent base, then 13 tons of material 1 will be used. Well, then how much material 1 will be left over? Well, there were 20 tons, so what's left over will be 20 minus 13 is 7 tons. The slack represents that amount, 7 tons. So the formula is right-hand side minus the left-hand side for the slack. So we could type equal to right-hand side minus the left-hand side. And that gives us the leftover amounts of the materials. In general, when the right-hand side value represents some kind of available amount of resource, then the slack will represent the leftover amount of that resource. Now, it will be interesting to try inputting some other numbers in here to see how much we could increase the profit without violating these constraints. We could see that with this solution, there's plenty of materials left over. So maybe we could increase this number. Oh, how about say 25? So that's still feasible, and the total profit now is increased to 1,300. Now what if I make this one 25 too? Is that okay? Profit has increased, but that is too much since you could see we have negative slacks, meaning we have gone over the limits, or that the amount being used is actually more than the amount available. This is the first half of the process, and before we go on to the next half of the process, I would like to just do a quick review of the different components of the Excel model. Remember that these two cells are the decision variables, and so that's the F and that's the S, and these cells are called in Excel language variable cells. And what is this cell? This cell is the objective function, and in Excel it's called the objective cell. That corresponds to this function. And the constraints are over here. The constraints are right here. Left-hand side of the constraints here, right-hand side of the constraints here. And you might say, well, what about this non-negativity constraint? This one. You don't have to explicitly add it to the model here. We're going to take care of this when we go to Solver. There's actually a box that we could check in a Solver dialog box that will add this constraint in for us. We need to remember that the model here consists of the decision variables, or the variable cells here, the objective cell here, and the constraints here. Now these numbers are not really the part of the model, but rather the data. These are the data we are using in the model. That is the coefficients for our model. Here we are assuming that everyone has Excel 2010 for Windows or Excel 2011 for Mac. If you have an older version of the Excel, you should download the new version. As you know, it's free to the paid students. There were significant changes in 2010 and 2011 compared to the older versions, so please don't use the older versions. In part B here, I gave you explicit instructions on how to access Excel Solver, because that's the thing that's going to solve the problem for us. It's a Solver is an Excel add-in that comes with Excel, but it may not have been activated. So you need to check your computer for Solver and activate it if you need to. Here are these steps with the screenshots shown here. For Excel 2010, I will also demonstrate it on my computer. In order to get Solver to show up on your menu, we need to go over to the File menu first, then go to Options. Then here we need to go to Add-ins on the left, then go to the bottom and make sure that next to the Manage box, Excel Add-ins is chosen, and then hit Go. Now you see a box with the list of add-ins that are available. Of course, your add-ins will have different items, but you should be able to see Solver add-in there. And it probably has not been checked like this, so you need to just click on the checkbox next to it to put a check there, and then hit OK. Now what? Now you should be able to find it in the Data ribbon, so go to Data tab and go to the very right, and there it is. In the Analysis group, you'll see it. So click on Solver, there it is. Here you could see that everything has been filled in already, but for the purpose of demonstration, I will reset all to erase everything so that I could do it over for you. So usually this is what you would see when you start from scratch. Okay, so what is the objective? Objective cell is right here. Do you want to maximize or minimize your profit? Of course, you want to maximize it, so leave the button for the max highlighted. Let's see where we are in the instructions. So this is where we are. And you could also see the picture of the dialog box in the Word file. Now the next item, variable cells. Here, variable cells are these two cells, B4 to C4. Now the constraints. Now in the constraints, for the constraints, I want to put these in, but I can't just enter these here myself. I have to click on the Add button. And cell reference is the left-hand side. You got the inequality type here, and constraint here is actually the right-hand side. First, I will show you the long way of doing this. I could put in each constraint one at a time. That's a long way. Let me do that first. So I go to the first constraint, left-hand side over here, less than or equal to, and then the right-hand side. So that's the first constraint. Now I want to add another one. Now I want to add a second constraint, so I click on Add. Second left-hand side, less than or equal to, second right-hand side, and one more for the third one. The third left-hand side, less than or equal to, the third right-hand side. So that's three constraints. When you're done, you hit OK. So here are the three constraints. So this is what you would do in general, add one constraint at a time. But here, because all the constraints are the same type, they're all less than or equal to type constraint, I could do all of them at once. Let me show you what I mean. To show you the shortcut, I'm going to delete the ones I did, and then click on Add. Now here, since all the constraints are the same type, I could do all three left-hand sides at once, and then all three right-hand sides at once. So by doing this, I've entered all three constraints, and Solver is smart enough to know which left-hand side goes with which right-hand side. Just gotta click on OK. So those are the three constraints. Well, what about the non-negativity constraint? For that, you just have to check off this box. Make unconstrained variables non-negative. So that takes care of that. And for the solving method, we are solving a linear programming problem. And for linear programming problems, Excel Solver uses simplex method. So here, click on the drop-down arrow and choose a simplex LP. So that's what you need to choose whenever you solve a linear programming model. So that's it. We got the objective function we want to maximize, got the variables cells here, got the constraints here along with the non-negativity. We are using simplex LP. So we're done setting this up. All we have to do is what? Oh, that's right. Click on the solve button to get that optimal solution. Now, how long do you think it'll take Excel to solve this problem? Maybe 2 seconds? Maybe 1 second? Well, let's see. There it is. That actually seemed shorter than a second to me. So let's see what it says. Solver found a solution. Well, that's great. All constraints and optimality conditions are satisfied. That means it found the optimal solution. Do you want to keep it? Well, of course you do. So let's click on OK. There it is. There is your optimal solution. So the optimal solution is right here. F is 25 and S is 20. And the optimal objective value, that is the maximum profit, is right here, 1600. So that we are going to call it optimal objective value. Whenever you solve a linear programming problem, you should always summarize the optimal solution and the optimal objective value. The optimal solution represents the recommendation, and the optimal objective value represents what you get if you follow the recommendation. We'll insert a text box for our summary. So the recommendation is to produce 25 tons of fuel additive and 20 tons of solvent base. And what do you get from this? You get the maximum total profit of $1,600. This will yield the maximum profit of $1,600. That is it.